All right. So thank you so much. Thank you for the introduction. My name is Wei Jie. I'm based in Singapore. I work with the Applied ZKP team with the Ethereum Foundation. And as Daniel mentioned, what we do is try to bridge the gap between research in zero-knowledge proofs as well as application development on Ethereum. So Semaphore is Applied ZKP's flagship project, which we started in mid-2019. And today we are super honored to have the opportunity to present our work. And we hope that this can start many productive conversations and collaborations. All right, so the problem statement is that privacy on public blockchains is hard. And while zero-knowledge systems like ZK Snarks can help this situation, it is still an uphill task for most developers. Semaphore attempts to address part of this problem space. It is a semi-generic privacy gadget for anonymous set membership proofs and message signaling. So it enables some use cases like mixers, anonymous login, and anonymous voting. And since developing privacy-focused applications requires highly specialized knowledge and skills, especially when it comes to ZKPs, developers who are not experts in ZKPs can choose to use Semaphore for certain use cases and sidestep a lot of the difficulty involved. Semaphore is currently one step away from being production ready. The code has been written, tested, and audited, and we are in the midst of phase 2 of our ZK Snark multi-party trusted setup. And once that is done, anyone can use it to build applications. And so developers can focus on building apps for users rather than worry about technicalities behind ZK Snarks, trusted setups, and so on. So let's talk about what Semaphore does. At the most basic level, it allows a user to, first of all, register an identity and subsequently anonymously prove their membership in the set of registered users. And when they broadcast, and when they prove their membership, they may also publish an arbitrary string. And this is what is known as broadcasting a signal. And the way that Semaphore is built is that they may only broadcast a signal once per topic per an identity. And we refer to such topics as external nullifiers, which we will cover in a later slide. Okay, so just one more level of detail. When the user registers an identity, they perform a transaction on the Ethereum blockchain, and this adds a leaf to an incremental Merkle tree as a smart contract. And this leaf is an identity commitment, which is basically the hash of an EDDSA public key and 2 random values. I'll go into more detail about these values in a later slide. And later on, to broadcast a signal, the user generates a zero-knowledge proof, which proves that they have the private key to the state public key and knowledge of these 2 random values. And the contract prevents double signaling to the same external nullifier by a single identity. I know that external nullifiers might be a bit confusing without going to a concrete example. So here's a super simple example of what external nullifiers do. So we have 3 users, Alice, Bob, and Charlie. And at T1, we see that each user broadcasts a signal to an external nullifier 1, 2, 3. And so Alice broadcasts 1, 2, 3, Bob does the same at T2, Charlie does the same at T3, and the signal is an arbitrary string. However, when Charlie broadcasts another signal to external nullifier 1, 2, 3, the smart contract rejects this signal because Charlie has previously used his identity Charlie to broadcast a signal to 1, 2, 3. So, but when Charlie does the same thing to a different external nullifier, Charlie's transaction succeeds. All right, so now just to take a step back, and because we are talking about ZKProof and talking about standardization and interop, external nullifiers is something that's within Semaphore that can be subject to standardization. So just a bit more detail. This is an example by Zhiqiang from the Ethereum Foundation about how an anonymous authentication application can use external nullifiers to allow registered users to log into services without revealing their origin identity. And because different services have different types, have different timestamps and different epochs, we need a standard for external nullifiers in order to make this work with different users and different services. Semaphore also allows you to have multiple external nullifiers and the ability to activate and deactivate them. So in summary, external nullifiers allow you to build different kinds of applications on top of Semaphore, as long as a use case is suitable for it. Now let's go into the technical details about exactly how the ZK snark for Semaphore works. This is a pretty high-level overview of the circuit. I just take a minute for people to read this before going to the next slide with more details. So we have over here, yeah, go ahead.
Just wanted to say that I think this is exactly what you have on the Miro board, right?
It is exactly it. So I guess maybe during the Q&A or anytime people are interested, we could switch to that board and we could draw on it. We'll just see how it goes, I guess. Anyway, these are like inputs to the snark, and the bold text are outputs. And these individual boxes are components within the circuit. These boxes themselves are circuits. So you have circuits within circuits, and the whole thing is a circuit comprised of multiple different circuits that are linked together. So let's look at exactly what this circuit does. So basically, this circuit proves three things. First of all, we want to prove that when we register an identity commitment, that we have a Merkle proof, that we have a valid Merkle proof to that identity commitment. And so that's the first fact to prove. The circuit hashes the information needed to create the identity commitment and then verifies a Merkle proof and checks whether it matches a Merkle root stored on chain in a smart contract. We also, skimming to number 3, verify that the signal was indeed broadcast by the user who generated that proof, and it does so using EDDSA signature verification inside the circuit. And finally, we hash something called a nullifier hash and output that value. And the smart contract has a mapping which allows it to prevent double signaling. Because if you signal to the same external nullifier with the same identity, what you end up with is the same nullifier hash. And so the smart contract prevents this from happening. All right, so I just linger here for a few more seconds for people to read this, and then I'll go to the next slide. All right. So from an attacker's perspective, they know that there is a set of registered identity commitments, but there's no way for them to link these ID commitments to the set of broadcasted signals. So this makes it ideal for use cases where users get privacy by hiding in the crowd. On the flip side, these applications require a large number of registered identities to sufficiently protect users' privacy. So for example, if there are only 2 registered users and 1 signal broadcast, the chances that user A made that signal broadcast is 50%. But if you increase the size of the anonymity set, then the probability goes down. A few more technical details about the components which comprise Semaphore. We build our smart contracts with Solidity, our ZK Snark circuits with ident3's circom language, and we have a helper library lib Semaphore and a demo application called Semaphore UI. And we use Kobi Gurkan's BN254 trusted setup code to generate our proving key and verifying key. So here are some sample applications built with Semaphore. A mixer is the simplest application for that we can achieve. And identity registration is a deposit of ETH or tokens. And to make a withdrawal, a user has to broadcast a signal using a proof of their initial deposit. And because external nullifiers prevent double signaling, it's not possible to double spend in a mixer. Another application is voting. So we treat each external nullifier as a new topic to vote on, and a vote is a signal broadcast to said topic. So one example is that at DEF CON 5, participants received an NFT, an ERC721 token, and we had a sample app that checked whether a user owned that token and allowed them to make an identity registration. And then later on, they could vote on topics, yes or no, to signal support or rejection of some controversial issue, which was just a demonstration app at a workshop. Finally, there is future work to be done on modifying Semaphore for rate limiting and spam protection. And so this is an extension of Semaphore, which I won't go into too much detail today. But basically, here's a link to an research post. It describes using Schemmer secrets sharing to disincentivize spammers such that their private key would be revealed if they were to spam a system, and that would have them be slashed. So when it comes to ZKProof, we might think about Semaphore as a combination of ZKP gadgets. And in the ZKProof reference document, we have a description of a few of such gadgets. So something we could think about is whether we want Semaphore to be included in this list of gadgets. But at least Semaphore uses Merkle-tree inclusion-proof gadget and a commitment gadget, as well as a signature verification gadget. All right, so here's a summary of the security claims that we uphold in Semaphore. So first of all, there should be no way to link identity registrations to broadcasts, and there should be no way to link broadcasts to other broadcasts. And only the holder of the private key used to create an identity commitment should be able to perform a broadcast in the first place. And that said, Semaphore is relatively new, so it's important to be aware and mindful of security risks. So let's go through those one by one. The first thing to be mindful about is that we are using 3 different hash functions for separate reasons. We use Patterson hashes to compute identity commitments. We use Blake2s to compute nullifier hashes, and we use MIMC sponge for our incremental Merkle tree. The reason for using MIMC is because it's efficient inside snarks, but we use Blake2s because it provides forward security against de-anonymization by quantum adversaries in the future. And we use Patterson hashes for the identity commitments because it's more secure than MIMC and less expensive than Blake2s. We are most concerned about the use of the MIMC hash function, and the Ethereum Foundation has a bounty on the security where they are paying out 20K and 10K awards for anybody who can break it. There are also other security concerns like front running. So for certain applications, like a mixer, we have transaction relayers that perform the withdrawal transactions for users so that users don't have to pay gas. It's important to note that for such applications, the sender's address, in this case, a relayer's address, is part of the signal. Or for example, part of a hash which is used as a signal. And this prevents front runners from grabbing their transaction from the mempool and broadcasting it under their own address and retrieving the reward that a relayer receives when they perform this transaction. But the main point here is that it's important to understand how Semaphore plays with the higher level protocol, whether it's Ethereum or any other protocol. All right, so I think this is something that I'd like to talk about and also discuss later in the Q&A, which is that there are a few things to be mindful about interoperability. So we can break this down into 2 main areas of concern. I'll address the general concerns first. So first of all, as mentioned earlier, we use the circum language to write the ZK snark circuits for Semaphore. But if anybody wants to implement Semaphore in a different language like Zinc or Bellman, it would be difficult because the compiled circuits won't match. So we have to think about how different ZK snark languages and frameworks can work together on a common standard. I'm aware that ZK interface tries to address this, but we think that it has to go further for it to be practical and for it to have some kind of production-ready implementation. And there is also another hot topic which was discussed in the previous session, in that everybody uses different constants for the hash functions. So for example, the circum lib library, which has a bunch of circum circuits, it provides a MIMC sponge circuit where the round constants are defined by using hashes of the text MIMC sponge. But this might not be the case for other implementations. And so this is something that hurts interop, and it's something we're concerned in the long run, because Graph 16 ZK snarks are not updatable, in that once you do your trusted setup, you have to do the whole thing again if you want to change the circuit. But when it comes to interop within Semaphore or specific to Semaphore, we can also think about the high-level API of the gadget, like what the inputs are or what the contract functions are. And as mentioned earlier, what kind of formats we want to use for external nullifiers. So trusted setups. So just a brief summary of how we are trying to achieve trust in the proving keys and verifying key for Semaphore. We are currently running a multi-party computation to generate these keys, and because these are Graph 16 ZK snarks, for this, we need to ensure that the toxic waste is discarded for the entire ceremony to be secure. And because we are using an NPC, we only need one participant to discard their toxic waste. We currently have more than 30 participants in phase 2 of our trusted setup. And we modified a user interface from the Aztec Ignition trusted setup. So anybody with Docker can run a command and participate in the Semaphore trusted setup. So I mentioned Aztec because Aztec initially built this infrastructure and user interface for a Plonk trusted setup, but we don't use Plonk, we use Graph 16. But thanks to the hard work by one of my colleagues, Brian Gu, who modified Aztec's program, we can run this and do a trusted setup for Graph 16 ZK Snarks. And so we invite everybody to go to this URL and have a look at the instructions on how to run it. It only takes 5 to 10 minutes and it's super fun. So nearing the end of this presentation, I'd like to propose some topics for discussion. So maybe we could think about whether we want Semaphore to be standardized and how that could be done. And we could also think about what are the different kinds of applications which people could build with Semaphore. And from a security perspective, we could think about hash functions. What are the security implications of using MIMC? And how do we gain confidence in snark-friendly hash functions? And also, yeah, so that's the end of this short presentation. I would love to discuss more and hear your feedback. Thank you so much.
Thank you. So maybe let's, before we jump directly into some of those discussion topics that of course are very important, we already have a note taker, so thank you very much. We would like maybe to open the floor to have any questions, maybe to clarify some points made in the presentation. Of course, this will lead us into the discussion, hopefully naturally. So anybody has specific questions? I know there have been a couple of questions. Kobi has been doing a great job to answer those on the chat, but maybe something that people want to ask as well. So I believe Guillaume has a question. Guillaume, would you like to ask that question?
Yes, hello. So my question was about the how the system scales regarding the fact that it has to check for nullifier hash that has not been used previously.
Yeah, we store the nullifier hashes in a mapping in the Ethereum contract. So there should be a bottleneck when it comes to storage, but it shouldn't be too severe.
Because it depends on the number of users, no?
Yeah, it does. That's right. I think that would be something interesting to benchmark. However, I think the gas cost for verifying proofs is much larger than the gas cost for storing the nullifier hashes. So it doesn't seem to be like the biggest scalability bottleneck in this case.
Thank you. I believe Kostas has another question. And by the way, Kobi, if you feel that some of the answer was left out from what you answered in the chat, then also feel free to jump in.
All right.
Kostas, would you like me to read the question? Do you want to?
Yeah, thank you for the first question on if it's
Hi.
only targeting Ethereum. And my second question is, which mode of EDDSA are you using? Because we have multiple flavors of EDDSA, right? We have ED25519, red DSA, pre-hash EDDSA. There are too many flavors of EDDSA. Do you have the answer on this? I mean, is it the one that it's in the RFC that NIST is trying to publish now, or something else?
We use the EDDSA circuit that's published with Circom. I can ask Kobi about exactly which flavor it is.
Yeah, sure. No problem. So
I think we should be worried about re-standardizing things that are already in the process of standardization.
Yeah, so that's a good point. So what we are using is based on RFC 8032 from the IETF. So it's essentially EDDSA with pre-hashing, but we have two differences. So we don't use the same curve. We use a different curve, which is essentially on Ethereum. It's called the baby job, which is based on how job was constructed on Zcash. So it's an inner Edwards curve inside the BN254 curve. But this can be generalized to any Edwards curve of the same form. And we are using a different hash function, which actually I don't remember if they specify exactly which hash function is used to hash the messages. I think they do, but we use a different hash function because of efficiency and because we relax one of the security properties for broadcasting. Then we opted to use the MIMC sponge variant rather than any of these normal SHA-256 Blake2 hash functions. So this is also maybe a good topic to discuss because we expect that many other circuit developers will need to do similar trade-offs or similar changes. And maybe it's good to have some guidelines for the community to do this securely.
Another thing that might need to be specified on top of existing standards is precisely which signatures are valid. So the RFC 8032, I think it is, doesn't specify, for example, what validation you do for public keys and signatures, whether you use cofactor multiplication, things like that.
Right.
If you do want a standardized hash that nails down all of those things, use red DSA. No,
I have a question about using different elliptic curves, right? In terms of interoperability, could two different Semaphore instantiations, say on different blockchains, for example, be compatible using different curves? Otherwise, this would somehow be a problem because a lot of the other blockchains that have kind of the different underlying curves.
YJ, do you want to take it or should I?
Go ahead.
Okay, so that's a very good question. And I think the answer to this is it depends, like all good questions. It depends on how you abstract Semaphore as. So if we aim, for example, to take this abstraction of using set membership plus nullifier computation plus signature verification and standardize this abstractly just to have it as a nice gadget that can be used for many different applications, then you could say that, all right, if we aim for some Semaphore instances to be interoperable, then you can use some hash that works for all of them. For example, for the identity commitments. But if you, or for the Merkle trees. So I answered similar question on the chat that Kostas asked. So related to that question, the question was, can it even be used on other blockchains? So the answer is related because currently what we require in order for you to use Semaphore, we need for you to be able to use memc on-chain, because you need to do some Merkle-tree computations when you add an identity. And you need to be able to store this nullifier map. So these are kind of two requirements that we have for this specific instance with this choice of hash functions, because of the performance requirements that we thought are the best for the application that we've seen. But if we aim for interoperability, you could say, okay, you could have this Semaphore SHA-256 that uses SHA-256 for, I don't know, everything, and then say, okay, this can work on both of these blockchains and work together.
And there is some hope for computing conventional hashes efficiently using PLOOKUP, for example.
Yes, I'm very hopeful for that.
With some caveats, because there's a lot of fixed overhead in the circuit to do that.
Yeah.
So it pays off if you've got lots of hashes.
Yeah, and I guess like it depends on the environment that you run it. So with Semaphore, we really want it to run, for example, on browsers and these kind of things. So we need to check like whether PLOOKUP approaches with the size of lookup tables make sense for these use cases. So
it's worth pointing out that if you have a proof system that can do efficient recursive validation, then your leaf circuit can use PLOOKUP, and you then actually prove a recursive verification of that. So it kind of is the best of both worlds. But that's not going to be ready until later this year, probably.
yeah.
Yeah. So I guess in that context, for an interoperability, the commit and prove would definitely be valuable, right? In some sense, if you could commit to all the identities somewhere under the same commitment and then use those identities in any blockchain or any instance of Semaphore for signaling on different blockchains, that could be valuable as a point for interoperability more than anything, I think.
Yeah.
Okay. Just a little incision. I want to make sure that we still have the note taker.
Yes.
Okay. Good.
But
sorry,
still,
thank you.
With this discussions, it's much easier if others also take notes, because
right,
very contextual. Yeah,
makes sense. So yeah, anybody who has answers to some of the questions, they're at the bottom of the notes. Feel free to add questions and answer them, or based on the discussion. There's more questions on the chat. So I think this one's specific to an application. Simon, would you like to ask your question on login use case?
Yeah, thanks. Just a quick question. But first of all, I love Semaphore. I've been following the project for a while, and it's really, really cool innovation. But I do have one question around specifically the anonymous login use case. So say if a user logs in, I would imagine they receive some sort of session token. If they decide to log out again, am I right in thinking that they won't be able to log in again until the external nullifier is changed? And if that's the case, then how often would you change the external nullifier?
That's a good question. So off the top of my head, you could deactivate an external nullifier. This would require some kind of like a coordinator's action. So the admin would have the ability to do that. But I think it also depends on the design of the system. So whether you want that to be based on a smart contract or based on an off-chain database, I think it would be more efficient if you had that off-chain for login use case, but if you wanted it to be on a smart contract, then you'll be bound by performance. I would need to think harder about exactly how a login system would work, because that involves like playing around with the external nullifiers. I think Kobi or Zhicheng, who might be in this group, might be able to speak more towards using Semaphore for authentication. Yeah, but I'm not super sure about that. I need to think more about it.
Yeah, no, I just, if it's a known limitation, it could be something that you could work with, but it'd be interesting just to see what, just to think about kind of how you work within those limitations and what you can build with it.
Yeah, it seems like it could be also sort of more of a trust issue on a central authority that is, right? Yeah. And actually, I have another maybe related question to this, but for the voting mechanism, where maybe another, correct me if I'm wrong, but a limitation that seems to me there. So the external nullifier would change per topic, I guess. So everybody would have one vote, or I guess maybe you, so if you only have one external nullifier, then it means you would not have coercion resistance per se. I guess you could define several nullifiers, but you would still have a finite amount of votes per topic or something like that. Okay, I see what
so
where
for
it's
the
going.
example, for the example, we have multiple external nullifiers, so you can vote on different topics. That Semaphore itself does not do any coercion resistance or collusion resistance.
I see. Okay. But I think in general, for the standard document, whatever comes out from the working group, it's important to have like an end-to-end application that we know. First we lay out what are kind of the privacy or the requirements from using Semaphore, and then make sure that that application fits those requirements. But probably the application itself will have more security to be proven or more privacy to be shown, right? It will be important to have such application as a motivation for the whole standard, right?
So if you ask me, I think the application that the Semaphore group, like the group that we've been discussing with more people on this, the main application that has been the focus was a mixer application. So
can we go maybe a bit deeper in that, just to get a clearer picture?
Sounds good. Wajid, you want to give an overview?
Sure. So for a mixer, the mixer is basically a smart contract that sits on top of the Semaphore contract and circuits. And the external nullifier is the address of the mixer contract. And we also define the signal that's broadcast as the hash of a few things, including the address that is the address that's designated to broadcast the transaction to withdraw the funds, like a relayer's address. So in this case, we do have the code for the mixer, and we also have like some description of it in the paper we submitted. Just off the top of my head, it's been a while since I looked at it. Yeah. Go ahead.
Yeah, so I think like you described it well. So like to recap that, like we have only one external nullifier, like in contrast to other applications like boardroom voting, you have one single external nullifier. So each user that gets added can broadcast once. And the users get added by a function that verifies that they send, for example, 1 ETH, like a fixed amount of ETH into the contract. And that's the requirement for you to get added into the group. So you're added, you add 1 ETH to the pool, and then when you signal, you withdraw 1 ETH to the pool, which goes to the address that you specified in your signal. So there is a very specific format for this kind of application.
Okay. Okay. Can I ask again how is the identity, maybe in, for example, in Ethereum, of the sender kind of hidden in the mixer? Maybe I missed it. It's basic, but.
You
Right,
mean?
so
Yeah. Okay. No. Go ahead.
The sender. So when it comes to identities, there are two identities. The first is the EDDSA private key that the depositor generated so that they can create an identity commitment. And the second quote-unquote identity is the Ethereum address that they use to send a transaction to deposit the funds in the first place. Semaphore only looks at the first one, which is the EDDSA key pair, because we are only concerned about the identity commitments in the tree. And when a relayer broadcasts a signal to withdraw funds, the signal is basically the hash of the recipient's address, the relayer's address, and the fee. And so this allows the mixer to prevent front running, so that only the relayer will receive the fee, and only the recipient will receive the funds. If that makes sense on a higher level.
Yeah. Okay. Think there is maybe one or two more questions. So I think one of them is maybe implied by the conversation, but I'll ask it anyway. What do the authors expect from a standardization process? So would you like to answer that question? Would you like to delegate that to the discussion?
I think from my point of view, personally speaking, I would like to hopefully be part of a process where we can bring something into production, so that people can have hands-on on published code that's audited and that works, and they can deploy to the apps sooner than later. So I guess that's my personal bias.
Okay. There's another question, which maybe is a clarification question. I think Markov sent this to me, but he meant probably to everyone. You claim that Groth 16 setup only takes 5 to 10 minutes. Which phase of the CRS generation is this? So I suspect it can't be the whole CRS generation.
So I think it's the second one, right? Someone told.
Phase 2.
Oh, I see.
Yeah.
Okay.
Yeah, we have about 60,000 constraints, so it's really fast.
Awesome. Okay. Any other questions from anyone who would like to speak up? Otherwise, we'll also go through some of the topics of discussion here. Okay. So I think one of the first questions that Wei Jie and Kobi Rose brought up were whether should Semaphore be added as a high-level gadget, as a framework, or and whether it's widely useful, right? So I maybe will answer first, just to kind of put it out there, that I think it's going to be important to abstract it enough for us to be able to use it in different settings and blockchains. So I think the idea of having the abstracted version where you're defining it in terms of primitives that kind of being plugged in makes sense to me. So I guess interoperability and security, right? Those are the two main goals of such a standard. And again, laying out then an instantiation of that with some primitives that maybe are already standardized, right? The question maybe is, should it be the most efficient primitives that are instantiated, or could we go with the standardized ones, right? So what's the trade-off that we want to take there?
So I think we should decide separately what primitives we want to standardize, and then only use those in higher level applications. We don't want to have the tail wagging the dog and have a standardized primitive only because it's used in the current implementation of some application protocol.
Yeah, I think what could be useful in such a standard is clarifying the requirements from each of these functions. So following, for example, what Zcash did, we know that for the Merkle tree, you only need something that is collision resistant. But that's already a good thing to know, that you can choose something that is efficient and only provides that, for example. And another point is that it could be nice to, at least when describing this higher level gadget without instantiating it, we could describe what are the security implications of having this hash broken or this function broken and so on. And then the people who instantiate the protocol can make their own trade-offs if they need more efficiency or whatever.
One comment I would say, again, this is very high level and probably it's a little biased coming from me, is that, I mean, the universal composability framework is here for, such a reason, right? You can define primitives, you can use it as gadgets in larger protocols. And if we put effort now, when we standardize even the gadgets or primitives to identify what functionality it represents, then when we use it in a higher level protocol, the security properties will translate at least as much as what UC will guarantee.
Well, to the extent that UC is compatible with the techniques that we want to use. Because in some cases we don't know how to.
Again, it takes effort.
Sorry, I missed what you said there.
I'm asking whether there is any viable direction for actually maybe proving security of this protocol under UC, under the UC framework. And I mean, this protocol has similar components as the Zcash. Muthu, you're being cut out for a second.
I was sorry. That's fine. I was just going to say that, identifying an ideal functionality is the first step. Like, what is it that you want to provide? Like, even with the semaphore or commit and prove, like whether we can achieve this definition, this can be worked, it can take iterations, take stages, and then, you can reach there. But what sort of functionality are you providing, right? I mean, you can, like, then at least we can, like, talk about certain security properties, reduce function collision or certain securities. Otherwise, we're just, talking in pieces, like how do they come together?
So I agree, it's useful to have clear specifications of what properties we need. But for example, as far as I understood, collision resistance isn't something that can be defined in UC unless you have a keyed hash. Is that right?
One doesn't quite have to define hash functions as an ideal functionality. You want to define higher level properties. And when you argue security, you reduce it to the security of collision resistance. It's not that you need to, of course, there are certain things that are hard to define in UC. For example, just digital signatures. You need to take quite a bit of effort to get there. But there is sort of a nice, there is, specifying like your higher level goal as a functionality, I would say is important. At least you want to say, these are the guarantees I would hope Semaphore would provide, right? And then you want to look at your protocol and see if it meets this definition. And you can at least identify, this is the part where we can't argue security fully. Is there an attack? If there isn't an attack, at least, you can argue something about it.
Would you be
Let me just give
comfortable
you
with sort of saying that the ultimate ideal, of course, is to aim for UC? I can't dispute that, but to maybe be more open to lesser models if we can't achieve it. For example, when we need to program the Oracle or that kind of situation.
Mary, maybe
also like
could you rephrase that? I didn't fully get that. I don't know if everybody did.
Okay, sorry. So Muthu is sort of bringing out a good point that UC is really very useful for building larger systems and saying, how do they interact? If they have these security properties, what does that mean? It's basically built for that. And really, we should be aiming for that if we can achieve that. I guess what I'm asking is, in this situation where we can't achieve that, and we do know of some situations where that's true, is there a maybe weaker model that we would also be comfortable with?
So still having this abstraction based on the requirements that we would want from the primitives without necessarily doing UC.
I mean, maybe it's sufficient to argue something more informally. An informal security argument is a lot better than nothing.
Yeah,
Sure. I mean, related to this question, is there such an informal argument that is maybe a hybrid of informal to formal? I don't know if there's a proof of security, but maybe Kobi and Vijay.
Yeah. So in the specification that we've shared, it's not really a paper; it's more of a specification. Then we describe what are the desires from each of the primitives that we use, and what would be the security requirements from each of them, and then the effects on the whole protocol. Maybe this could be refined.
Okay. So yeah, I think that definitely it's important to have some sort of security argument, right? And if we move in this direction, then this means that we're looking at the four different primitives, right? So trying to generalize that for their requirements. Would the requirements change per application? That's maybe an important question to keep in mind, because if we're standardizing Semaphore for one specific application or for more than one application, right?
I think the goal is that you standardize or agree upon the specific abstract protocol of Semaphore. And the whole goal of Semaphore is that you don't need to touch that protocol once it's instantiated. So different applications should be able to use the same instantiation. Like you now develop login, then you can use that one. And now you develop mixers, you can use the same one. That's the idea. So the security requirements should not change. But what should change is maybe for efficiency reasons, you want to instantiate it differently. That's the goal of this.
Well, I mean, we did sort of, I mean, between the login application and the e-voting application, it seems like the external nullifiers are generated in a different way. And I'm wondering whether
Yes.
that does give for a different kind of requirement, security requirement, maybe.
Yeah, that's a good question, because this is definitely part of the application. And for different applications, you're right, you do have different security requirements. In the mixer, you even dictate the content, the format of a signal, not even only the format of the external nullifier. So
Right.
It really depends on the application. And maybe you could argue that that is a good reason to focus on the lower level protocol rather than the upper level application, but have enough confidence that it satisfies or suffices for enough applications.
So basically we will have to, in the standard, have at least 2 or 3 applications that generalize enough the use of Semaphore to highlight all of these different cases, right?
Yeah.
Not all, maybe some, to at least be a template or example for others.
Yeah, and we definitely want to hear from more people of how they could use this above of what we already thought and other people worked on. So that could be helpful for the process.
So on the topic of standardizing SNOC-friendly primitives, these are probably going to be primitives that are shared across several of the protocols within the standard.
Yeah.
So it probably doesn't make sense for lots of different working groups to duplicate that role. Do we want a working group that is specifically for that?
I agree with that. Yeah.
For example,
Yeah.
the commit and prove needs SNOC-friendly commitments.
Yeah.
Yeah, and I think many other protocols that or applications that are not part of ZKProof right now that do need this or aim to have this secure. I know of at least 3 off the top of my head.
Okay, maybe I would suggest in this topic to start a separate conversation, maybe after this discussion, maybe offline for now, to see how we can put that forward. Because if it's something, right, and it is that is going to be part of other discussions and other proposals, we don't want to have that kind of loophole there that sort of invalidates a lot of the uses. And it's something, as Kobi is saying, that is widely used. Maybe one of the things in zero knowledge that is used mostly across projects. So it's worth thinking of. Kobi and Dara, is it okay if I just create a side channel for now and start discussing that for next steps?
Yeah, sure.
Okay. Of course, anyone who wants is more than open to join that. Okay. Does anybody who hasn't spoken yet would like to say anything? Maybe how they would see Semaphore useful for them, or any other issue that they would find when using Semaphore, even maybe from the user perspective, things that they would think are important to keep in mind.
I will personally stick to my original question that Interoperability is very important here.
Yes.
Let's say we want to use it, right? Let's assume, I mean, it's very interesting, even for me or the crypto team in general in our case. But if we cannot use it because of algorithm, let's say, non-compatibilities, then we can do nothing. So yes.
But can you be more specific? Like, can you be more specific?
So
how would you
example,
like the interoperability to work?
So even for example, if there were some options for per blockchain, like I know, for example, now they have this custom EDDSA thing, which is different from what we use in Libra, for example. And we cannot force people to have different signature keys against, and especially if they're using HSMs and other stuff, it might be completely out of the game. I mean, we cannot do it. So at least if there were some gadgets which are more standardized, even if they're slower, it would be super helpful for the community to use it even in other contexts, not only Ethereum, right? Ethereum is one application, I get it. But if you want to get it in a more broader sense, like other blockchains like Hyperledger, even Corda, my previous place, now Libra or other places or other blockchains, we need a way to be compatible, to at least have an option in the gadgets that is compatible with the current settings. Or at least it's more standardized so people can use it. Because now even to go through the specifications of what is this custom EDDSA algorithm, it takes time, right? You need an extra team to work on this, to read more about this information, why the key is different than what we use. It's very important if we can have a more, either more options or better documented selections on why did we do that.
I think it's a great point, and this is exactly good feedback that we need to have and to see how to generalize this or how to modify this to sit to this kind of needs. And for example, the HSM is exactly a very good point because, yeah, you know, there are HSM which are programmable and then you can put any curve you want, but the industrial HSMs or the ones that are the most bulletproof maybe cannot be programmable. So we need to see how to generalize the protocol so that it can also use these kind of things.
So
exactly.
Just to put,
yeah.
I was about to say, like,
yeah, go ahead.
Yep.
Go.
After you.
Okay, cool. So my question is it possible that we are going to have two different circuits? So someone can pick their own, because you don't want to create a huge circuit, I guess, right, with so many options. But it might be wise to have two different options. two different things that people can use it in one context and some others in the other context. Even if these are not interoperable now, at least you know it's supported in your own system.
So if you ask me, I think this should be done on two levels. So first of all, we should agree on the abstract protocol of this, then that's useful enough. And then we can see how to instantiate the different parts differently. And if we're talking implementation-wise, like this is something that maybe the community could work on, like the Semaphore community, so that you could have these kind of options. So like you say, definitely not in the same circuit, so you can choose in the circuit, but probably it's something that you choose while you do the setup for the circuit. Yeah.
So the only bit I was about to say was about HSMs. So generally speaking, you know, if the industry needs to adopt any of those things, the current level, forgive me for saying this out loud, like current level of maturity we have, because you know, if there's any certification that's required, it's a very long ball game, and they need to commit forward a lot amount of resources. So I don't think we are anywhere near any standards that we can give, like for FIPS or anything like that. I've been involved in building applications with HSMs and, you know, Standardizing committees. So this is like a complete nightmare as it stands right now. Until we get to the stage, I am not sure any mainstream HSM providers would be that keen. 2 cents.
Yeah, this seems to be a generic problem for protocols on blockchain, not only to Semaphore specific.
Yeah, completely agree.
I mean, I don't think this should be included. Maybe it's my personal opinion, but I don't think this is this should be within the scope of the standard. Maybe a mention to it, but not specifically say how you would store these values on HSMs or other hard wallets, for example. Right? I mean, maybe it's just me. If anybody else has a strong opinion on that. Okay. There is another interesting question here that someone added. Should we consider recommending a method of detecting if the system is being attacked? This can in general be problematic in perfectly hiding schemes. So can we build or can we have such a system for detecting whether someone is attacking Semaphore?
It's a very good question, because there are some attacks that I assume are not detectable. If you know, for example, the toxic waste in the trusted setup is somehow revealed, all the participants are dishonest, and we use, for example, the mixer case, then someone can just create a proof that they can withdraw some ETH and withdraw it, and it will be indistinguishable from
Come
a
in.
normal proof.
Come in. What's the problem?
Markov, I think you're on. You're not on mute. So.
Yeah, my baby unmuted.
Okay.
Yeah.
So yeah, but there are maybe other attacks that could be detectable. But yeah, I'm curious to hear what the asker had in mind.
Yeah, same here. I don't know who asked the question. Does anybody recognize this question?
It was in fact my question.
Okay.
Oh, awesome.
So I sort of had in mind that you have a little bit of a trade-off between something which is perfectly hiding and cannot possibly be broken, and something where there might be trusted parties involved that can decrypt some of the information. I don't know a way of achieving it without doing that. And I guess what I'm asking is, do we consider the perfect hiding to be more important than the than being able to detect attacks?
Okay, got it. That's a good question. Well, you're right that this is something that we chose to focus on hiding in these designs and all the applications that we've considered. But maybe if more people have ideas for applications that could benefit from less hiding and more detectability, that could be interesting.
So is it only the commitment schemes that is determining that property?
I don't think so. I think it would. I think it would be the proof system as well.
Oh, I see. Okay.
If I understand Mary's point, yeah, sorry.
I was going to say that we probably should define commitment schemes that are one that is perfectly hiding and one that is perfectly binding, for example.
Yeah, that's a good. Yeah, but for the attack that, for example, I mentioned of just creating a proof with the toxic waste, then you still have zero knowledge, but yeah.
But you know, this isn't just specific to systems with trusted setup. Like even with a transparent setup, there could be any number of ways that your system could get broken. And if you don't know about it, that is a problem.
Yes, I completely agree. This was just an example. Yeah.
Yeah, I mean, I think in general, this is a very interesting question. I don't know if there's been a lot of ways to study it or other work on it, but can there be ways to detect, right? I think sharks, for example, is an example of that, right? Like you can detect whether proof or a set of keys have been compromised.
So yeah, I guess like that comes to Mary's point that that was one example of an attack because of the proof system, but even in transparent system you have those. Yeah.
Right. Maybe in this context of attacks, I was thinking about all the applications that we were discussing, and it seems like there is always some kind of like a trusted central party. Maybe generating the external nullifiers or maybe generating the identities and so on. How do we see that being as a problem to the real deployment of these applications?
So it depends on the application because, for example, in the mixer case, you don't have a central server, you don't have a trusted party. What you mentioned, the some nullifier is just the address of the contract, and that's generated during the normal provision of Ethereum. And I would expect that it really depends on the application of who is authorized to change these parameters. So when you talk about some kind of boardroom voting things like YJ mentioned that has been done in the workshop, then you could think of, all right, the conference organizers has the admin key to add new questions, but maybe, it could be another Semaphore instance that has some stake in it that votes on which questions are added. So you could think about it being done in a more decentralized manner depending on the application. So
more recursively or something like that.
Yeah, I mean, like you could also do it like just with a DAO, for example, that decides on the questions that are added.
Yeah, I mean, it's a governance question, right? Whether you want to add something or remove it, and whether you want to have a single party to trust. Voting mechanisms are fine, I guess.
Yeah.
Okay. Muthu, is there anything else right now that you have in mind? I actually think Muthu may have left, so not Muthu. But does anybody else have anything in mind? I mean, there's, I think, a couple more questions. Okay. Let me just go through this. So maybe we can discuss kind of what should be the first milestones of the working group. So again, I encourage everybody in this discussion, especially if you have some kind of interest or stake on seeing Semaphore being adopted, to join the working group, because this will allow us to get the proper input for interoperability and ensure security and so on in the standard. So we basically, just to kind of quickly summarize, and of course I may be forgetting several topics, but we discussed the several ideas, right? One is we want to abstract the protocol from the primitives, and I think this is kind of a recurring theme in the different proposals. We also saw that with Costas on last Monday. We want to abstract the protocol, and we want to make sure we give the proper requirements there. We also want to have at least one or two applications that cover different ways of generating the external nullifier, for example, to have them as examples for users. I believe we said we're gonna start a kind of separate working group just to look at snark-friendly primitives. And the question is, what should be kind of the first milestones, really? Maybe in the next couple of months, right? That we could see from an initial draft or a revised draft. Because again, I guess maybe something to remind again is that the paper that was submitted does not necessarily have to be the standard that is created. In some sense, we may adapt the format, that we may create a template for a standard or whatnot. I will say that the spec that was accepted to this workshop is pretty good in terms of presenting all the different parameters that are used and instantiating the different primitives. But again, we will have to look back at that and see how much we can abstract and how much more work needs to be done there. Maybe YJ and Kobi, you have also a couple of suggestions on milestones, maybe more concrete.
I like the milestones that you presented. Like I think that moving this forward would include making the abstract protocol and see that it suffices for applications that the participants in ZKProof have in mind. It would there was the topic of snark-friendly hashes and so on, like you mentioned, and there could be a discussion on how to instantiate it for different scenarios, and what are the more precise security requirements, rather than, for example, just a cryptographic hash function, just an EDDSA signature. Maybe we could be more precise about the security requirements so that we could allow for more flexible instantiation.
I will also add to these milestones at least a discussion on the point that Mary brought up on detection of attacks, potential detection.
Yeah, that's very interesting to discuss.
Okay. Sounds good. Maybe as a last point of mine, I guess we're also coming close to the end, but how would we want to set up a way to test whether this standard is being used, whether Semaphore is actually being adopted, aside from like input maybe from the communities? That is there a way we could try to do that? Maybe centralizing a reference implementation. We didn't really get to talk about the implementation, although I know that we thought about doing that for a bit. Maybe we could put that as a milestone of ensuring that the implementation details are kind of agreed upon.
So we have an implementation online in our GitHub, and I wouldn't say it's like a reference implementation because I'm not sure how we would define a reference implementation, but for what it's worth, the code has been audited, and so I think people would be attracted to code which has been audited because it takes resources to get to that stage.
So maybe that's a question. Yeah. Like, should we abstract some of that code, like maybe restructure a bit to allow for people to use that and maybe plug in different primitives?
Yeah, that makes sense. Something that I'm not sure if this like fully answers the question, but we have explored using the Poseidon hash function in place of MIMC, and we know that works. It's just a matter of changing swapping out certain circuits.
So yeah, at the very least, maybe guidance could be provided of how to do these kind of things.
Right.
Yeah.
Yeah. Okay. Okay. Anyone else would like to add another point? The same topic, different topic. There is still time to speak if you haven't spoken, and to say whether you would like to use this or what is your interest, your application of interest. Okay.
I would be super interested to hear about ideas for different applications beyond voting and beyond login and beyond mixers.
Yeah, me too, actually. That would be very interesting. How does the yeah.
Sorry, the protocol, if I understand it, is quite similar to Zcash or Zerocash in some respects. Do we want to standardize a kind of a toy cryptocurrency, shielded cryptocurrency protocol?
I'm wondering though, can Semaphore be used for token transfer per se?
I think that in the current protocol, it will be hard to do like shielded transfers, like very much like in Zcash or Zerocash, because the structure is different enough. It's not compatible with how Sprout works, and it's not compatible with how Sapling works. But maybe this is something we could think about. Yeah.
Yeah, I wasn't exactly sure how similar it was. If it was something that could be done relatively easily as a demonstration, then yeah, but we don't want to be inventing our only thing that probably will not get sufficient usage and sufficient security analysis.
Yeah, so yeah, definitely a topic to discuss.
Yeah. Okay. I will say in this respect that we probably want to try to limit the applications of Semaphore to those that use the protocol as is, in some sense. Like,
right,
keeping the protocol as simple as possible for a standard will be easiest, at least to get it to an agreement on the standard that is secure and interoperable. Right, we know that, I think we all know that the more complex a protocol becomes, the harder it is to make it interoperable and prove security. So,
Yeah.
Okay. Awesome. Any maybe final words, Kobi, Weijie, anyone else who hasn't spoken or who has spoken? I'm still wondering why other people don't speak, but I'll keep those thoughts to myself.
Yeah, I'm writing. I'm trying to.
Yeah. Thank you, Markov. You definitely speak and write, and it's amazing. So, but if you have some comments.
Yeah. Thank you, everybody, for attending and your amazing questions and the amazing discussion. I think one last thing is from me is an invitation to join our phase 2 trusted setup. The URL is in the slides, and we would love to have you participate. Please reach out if you have any further questions offline, and if you want to sign up to take part in the ceremony.
Great. So thank you all very much. Thank you to the speakers. Thanks to Muthu, who was moderating, to Tal for the great keynote, and to Yao for leading us into great discussions. I'm going to stop the recording now.